Good evening, everyone. Welcome to today's session. Hello. Uh, we'll wait for a couple of more minutes for the participants to join, and then we'll move into the question discussion. So, hello again. Welcome to the 10th week of the problem solving session. Today, we will be looking into the some of the sample problems that will help you deal with the assignment 10th, which is associated with the lecture series of the week 10th, that involves lectures 45 to 49 on groundwater resources planning and management. So as always, you will be shown some questions on the screen and you need to answer it uh, by typing in your answers into the chat box. And then once I get your answers, we can move on to the um, solution discussion or discussion of the question, the theory behind it, and everything like that. So let's move to the first question. Which out of the following is also known as the structural measure in scientific management of groundwater resources? Options are demand side measures, supply side measures, scientific measures, or is it none of the above? Okay, so let's move to solution. So here we are talking about what is called a structural measure when it comes to scientific management of groundwater resources. So as you can see here, now groundwater management of groundwater resources is something which is very much necessary in today's world because of the scarcity that we are facing when it comes to the groundwater resources available. There is also immense pollution of the groundwater resources that is making it not good enough to be used. And again, the availability of the groundwater, whether it is a renewable or non-renewable resource, because we have seen how groundwater travels. It travels at a very slow rate. So whether we'll be able to preserve groundwater for usage in the coming future, all these are major issues that are faced by the world and even by a country, particularly when it comes to groundwater resources. So in order to bring into strategy some measures to preserve and conserve groundwater. There are groundwater management techniques and the scientific all the strategies. It is necessary that we look at the issue in a scientific point of view and develop scientific management techniques for the preservation of groundwater resources. So, when it comes to groundwater resource management, the scientific management of groundwater resources are a combination of two things. One is management techniques that focuses on how the groundwater can be supplied. That is, the supply side measures undertaken, and how the groundwater can be managed when it comes to the demand of the ground. Management techniques that is taking into consideration the demand of the groundwater. So it is a combination of both of this that will help us in achieving a proper management technique of groundwater resources. So under the supply side measure, like we said, it is regarding how much of water can be provided in the form of groundwater to people who need it. So supply side measures focuses on increasing the extraction of groundwater resources based on its availability. And demand side is how when groundwater is being used, I mean, according to the demand, how can we use it as well as preserve and conserve it without taking care that much wastage is not there, or how can we save it from pollution, are all the measures that come under demand side measures. And the supply side measure is also called as structural measures. So the question here was which is also known as a structural measure in scientific management of groundwater resources. So the correct answer is option B, supply side measures. So supply side measures is also called as structural measures in scientific management of groundwater resources. Second question. According to the most recent guidelines established by the Central Groundwater Authority, industries are required to construct a groundwater monitoring telemetry system based on how much volume of water they are extracting. So when industries are extracting a certain amount, if it is extracting a certain amount of water or greater than that amount of water, they are supposed to install a groundwater monitoring telemetry system. So what is the quantity of groundwater, I mean the threshold or the limit of water that has to be extracted if the groundwater monitoring telemetry system is to be set in place? What is the guideline for setting up a telemetry system? I said 5 cubic if 5 cubic meters of groundwater is extracted, should they set up, or is it 8 and more, or is it 10 and more, or is it 12 and more cubic meters of water? If extracted, a groundwater monitoring telemetry system should be placed. Okay. So there are, like I said, there are certain guidelines, regulatory guidelines that are in place so that there's proper management of the groundwater resources, and this is set up by the Central Groundwater Authority. And according to the Central Groundwater Authority, if an industry is extracting more than 10 cubic meters of water, then they are supposed to install a groundwater monitoring telemetry system. So this is how the guidelines go according to the Central Groundwater Authority. So the answer for this question would be option C, 10 cubic meters. Moving on to the next question, which of the following is a major source of groundwater recharge? So this portion has been covered in the previous week, where we had looked into confined and the recharge happening in confined as well as unconfined aquifers. So how does unconfined aquifers get recharged naturally, and how are confined aquifers recharged naturally? So the answer will be in that. If you think about it, you know the answer for that, then this answer is pretty much related to it. Okay, moving on to the solution. So, like I said earlier, we have seen how unconfined aquifer, which is one of the major sources of groundwater for us, is recharged. The water from the precipitation or rainfall, when it hits the surface of the earth, it will infiltrate into the soil, and it will go down and join the or enter the water table or accumulate into the water table of the aquifer. So this is one way of how groundwater is recharged naturally. So major source of it is coming from rainfall. Then there are also situations where rivers and lakes or streams are providing water into the groundwater table, which is called effluent streams. This is also something we studied in the earlier problem solving sessions and said in earlier lectures. But a majority of the groundwater recharge is taking place through rainfall. Recharge is occurring as a result of rainfall. So the correct answer for this question would be option A, the rainfall. The fourth question, how much area in hectares is called a watershed? Is it 10,000 to 50,000, 50 to 1 lakh hectares, 50 to 2 lakh hectares? This is 1,000 to 10,000 hectares. Okay, so now for the purpose of groundwater management, it is required that we divide the area that is under consideration into some general units. We have also studied in the previous problem solving session about groundwater assessment units. Similar, one of the units or the sub units is watershed. So it is necessary that we subdivide regions into some standard units based on the area or based on some criteria, so that the management is feasible or possible in a more sensible way. So watershed is nothing but watershed is something into which, I mean, an area where all of the rainfall that is occurring will drain into the rivers, and all the rivers are going to join one outlet point. So whatever rainfall is occurring in that area, that all of that rainfall is going to reach a network of rivers and streams, which will flow and reach an outward point. And one watershed is generally characterized by a ridge line, a high line surrounding, so that all, that it is because of that slope also that water is all falling into it and then flowing to the river and reaching one outlet point. So that is basically what a watershed is. Now, based on the area, watershed can be classified as watershed, sub-watershed, milli-watershed, micro-watershed, and mini-watershed. Now, here the question was based on how much area is a classification called a watershed, and it is 50,000 to 2 lakh hectares. So, if the area covered is, I mean, area into which all the rainfall is drain or rainfall is flowing into drainage of network drainage is coming in between 50,000 to 2 lakh hectares, then it is called a watershed. If the area is between 10 to 50,000, then it's called a sub-watershed. 1,000 to 10,000 milli watershed. 100 to 1,000 is called micro, and 10 to 100 is called a mini watershed. So this is the aerial classification for watershed. Our question was based on how much area is an area called a watershed, and it is 50,000 to 2 lakh hectares. So the correct answer is option C. Okay, moving on to the next question. How much area in hectares is would you call a watershed, a micro watershed? Just now we looked into all the classifications. So it's watershed, sub watershed, milli watershed, micro watershed, and mini watershed. So based on how much area is it called a micro watershed? So let's see what the answer is. So the correct answer is option C, 100 to 1,000. So let's go back to the watershed classification once again. 50 to 2 lakh, we know it is called a watershed. Then 10 to 50 is called a sub. 1,000 to 10 milli, 100 to 1,000 micro, and 10 to 100 mini watershed. So the question here was how much area is involved in a mini watershed. So it is 10 to 100. Sorry, micro watershed. Micro watershed is 100 to 1,000. So the correct answer is option C. 100 to 1,000 hectares contribute to a micro watershed. Moving on to question number 6. What is the major goal of the supply side measure for scientific management of groundwater resources? So we did mention about why we need groundwater management. We also went through a slide that talked about what comprises of scientific management of groundwater resources, the supply side measures and the demand side measures. And supply side measure is also known as structural measure. So here, what are the major goals that are involved in supply side measure is a question. Is it controlling groundwater resources, protecting the groundwater resources, increasing extraction of groundwater based on its availability, or is it conserving groundwater resources? Which of the following comes under supply side measures adopted in scientific management of groundwater resources? Is the question. Yes, so let's move on to the solution. So the supply side measures are focusing at how the management techniques that is related to providing water. So definitely it is increasing extraction of groundwater depending on its availability are the major goals of supply side measures in scientific management of groundwater resources. And the demand side measures are aiming at how to control, protect, and conserve the available resources. So, supply side is looking at how much of water can be extracted or how to increase water extraction based on the availability. And demand side is taking into account or aiming at conserving, protecting, and controlling the usage of groundwater resources. So the correct answer for this question would be option C, increasing extraction of groundwater based on its availability. The other three, controlling, protecting, and conserving, is coming under demand side measures of scientific management of groundwater resources. Okay, so moving on to the next question. Wastewater return is an example of indirect recharge. Is this statement true or false? So we pretty much looked at various methods in which groundwater can be recharged naturally as well as artificially. This here is the focus is on indirect recharge. How is wastewater return an example of indirect recharge or not? Okay. So the correct answer is option B, false. Wastewater is not an example of indirect recharge. So recharges can be broadly classified into artificial, natural, and indirect recharge. Artificial recharges that is occurring as a result of irrigation losses or seepage from canals. Then wastewater return. Wastewater return is method of art, not a method, but it comes under artificial recharge. Now, natural recharge includes recharge of groundwater as a result of rainfall, as a result of seepage from surface water bodies like effluent streams. Now, indirect recharge is nothing but an aquitard leakage. So, we have studied what an aquitard is. An aquitard is something that is capable of transmitting water, but not as significantly as that as an aquifer. So they are also called leaky aquifers because vertical movement of water is, or vertical means not exactly vertical, but through these confined through these layers, water can pass through them and reach the confined aquifers. So this is one method of indirect recharge. Aquitard leakage is an example of indirect recharge, whereas wastewater return is an example of artificial recharge. So the correct answer for the question would be wastewater return is not a method of irrigation, indirect recharge. So false would be the correct answer. So you can type in your answers in the chat box and then we can discuss the solutions. Eighth question would be, which out of the following does not fall under the demand side measures for scientific management of groundwater? So this is again something that we had discussed in the earlier slides, what is supply side and what is demand side. So the question here is which does not fall under the category of demand side measures. Is it the judicious utilization of resources for ensuring its long-term sustainability, ownership of groundwater, need-based allocation, pricing of resources, or extraction of groundwater? So let's move to the answer. So we had talked about the supply side measures of scientific management of groundwater resources. Supply side is taking care of how much of water can we provide or increasing the amount of water that can be supplied by increasing the extraction depending on its availability. And demand side, on the other hand, is focusing on the a judicious utilization of the water that is being extracted. So that is involving the controlling, protecting, and conserving the available resources. So how can it be done? It can be done by taking ownership of the groundwater. So if we know that the groundwater is a resource that belongs to us and we are careful about it as an entity that belongs to us, then naturally that instinct to save that will come. Next is by pricing groundwater based on the needs of people. So need-based allocation pricing of the groundwater resources. Then involving stakeholders in various aspects of planning. So if there are policies and techniques or people that are investing in the management of groundwater resources, that can include individuals, that can include organizations or companies or whatever, also involving them also in the planning will help in management, help in getting more ideas and implementation of these groundwater management techniques. Then proper monitoring and also efficient and effective implementation of these policies that has been developed, regulatory measures that have been developed. Effective implementation of that would also help in conserving, protecting, and controlling the use of groundwater resources. So all of these come under demand side measures, whereas in supply side, it is more focused on how you can increase the supply of groundwater, how you can increase the extraction of groundwater or provide groundwater. So in here, except for the option D, all of them is talking about the demand side measures, judicious utilization of this resource for ensuring long-term sustainability, taking ownership of the groundwater as a resource, and need-based allocation pricing of resources, except for extraction, which is a supply side measure. So the correct answer for this question would be option D, extraction of groundwater. Now, chlorinated hydrocarbon is a qualitative issue in water resource management. Is the statement true or false? Okay, so let's move to the answer. Now, what is this qualitative issue and what is this quantitative issue? Now, although there are a lot of policies and lot of strategies and lot of management techniques when it comes to water resource management, there are a lot of problems also we encounter when like implementing all these policies and techniques and all. And so the shift has been majorly onto sustainable water resources management, which focuses on being able to use the resources sufficiently, as well as preserving or conserving some good amount of resources for future needs also. So it is not only taking care of the present needs, but it is also taking care of the needs that will be encountered in the future. So this is what is called sustainable water resource management. Now, there are sustainable water resources management. Also, there are non-sustainable methods that is only taking care of the short-term, uh, that involve only short-term management issues, or short-term management techniques that will only take care of immediate requirements. So such practices are non-sustainable, and these non-sustainable practices face quantitative as well as qualitative issues. Quantitative issues are issues that are relating to how much of quantity of water is affected. Qualitative issue is nothing but the issues that are related to the quality of the groundwater. So quantitative issue is again overpumping, destruction of the wetlands, salinization of soils and water resources comes under quantitative issues. And qualitative issues include the contamination, the salt in groundwater, chlorinated hydrocarbons in groundwater. All these are issues that are related to the quality of the groundwater and are called qualitative issues. So question here is a chlorinated hydrocarbon a qualitative issue in water resource management? It is a qualitative issue along with the contamination of groundwater and a lot of salt in the groundwater. It's also qualitative issues in water resource management. So the correct answer is option A, true. Moving on to question number 10. Which of the following is not a quantitative, non-sustainable issue of water resource management? We just went through the theory about what is qualitative, what is quantitative issue. So out of this following, which is not a quantitative issue? Okay, moving on to the solution. We just now checked what is qualitative quantitative issue. We'll go through that slide once again. Here, non-sustainable practices are encountered with quantitative as well as qualitative issue. Quantitative issue includes overpumping, destruction of wetlands, salinization of soils as well as water resources. And qualitative issues are associated with contamination, salt, and chlorinated hydrocarbons. So the question here is which out of the following is not a quantitative non-sustainable issue, and it is contamination of water resources, which comes under qualitative issue. The other two are quantitative issues. So correct answer is option C for question number 10. Moving on. Which is the first state in India to have made rooftop rainwater harvesting structures compulsory for all the houses across the state? Which state in India made it compulsory for all the houses? I think pretty much after that, many of the states have adopted this making rainwater harvesting a mandatory. But which was the first state to implement this? Okay. So Tamil Nadu is the first state to make this the rooftop rainwater harvesting structure mandatory across the state. So this initiative was introduced in the year 2003, after which a lot of other states also took this model and implemented in their respective states. So the correct answer for this question would be option C, Tamil Nadu. Moving on. Which out of the following is not a qualitative issue regarding non-sustainable practices of water management? So which out of this is not a qualitative issue? Again, this is some previous questions that has been interchanged and asked. We looked into what are quantitative problems, what are qualitative issues. So which out of this is not a qualitative issue? Is it contamination, overpumping, salts, or chlorinated hydrocarbons? Which does not come under qualitative issue. So those of you entering in between can given your answers in the chat box if you know it, so that this would be more of an interactive session. Okay, so this is again something that we looked into. Qualitative issues include contamination, chlorinated hydrocarbons, and salts. And quantitative issues include overpumping, the destruction of wetlands, etc. So overpumping comes under quantitative, not qualitative. Moving on. Which of the following is a conjunctive use program in groundwater resource management? Is it rainwater harvesting, lining of canals, storing surface water into underground formation as groundwater for future use, or none of the above? Which out of the following is a conjunctive use program in groundwater resource management? Is rainwater harvesting a conjunctive use strategy? Is lining of canals one? Storing surface water into underground formations? Or none of the above? So conjunctive use is nothing but a coordinated management technique of managing the surface water as well as groundwater, so that there's a maximum yield in total water resources. So it is making use of surface water management techniques as well as groundwater management techniques, so including surface water bodies as well as groundwater bodies together, so that totally the water resources can be managed. So out in this conjunctive use program, one of the established work is storing the surface water in underground formations, like we had studied in the previous problem solving session regarding recharging dug wells as one of the artificial recharging techniques. So surface water is stored in these underground formations, so that in the future we can use it as groundwater. So this is one conjunctive use programs when it comes to groundwater water resources management. So the correct answer for this question would be option C, storing surface water into underground formation as groundwater for future use. So like I said, conjunctive use is nothing but that includes surface water as well as groundwater management techniques, and surface water bodies as well as groundwater bodies are included together to develop management strategies. Moving on, which of the following is a major step involved in watershed modeling? So what are the major steps involved in watershed modeling? Is it formulation, calibration or verification, application, or all of the above? Okay, so moving on to the solution. So watershed modeling is nothing but when it comes to water resources management, we saw how an area is classified into a watershed. What is a watershed? How an area is classified into watershed, or based on what criteria? And also one of the major and important steps, or not important steps, yes, you can say it is an important step as well as an important tool that helps in more effective groundwater management or water resources management, is the ability for us to model a watershed. So we can make a model, a numeric, we can make a software that will help us in modeling a real-time watershed in computers, so that we can estimate or we can predict the amount, we can scale what is the actual condition to a smaller level, and run these models so that we can predict what are the what how much of water resources water will be available in the future, and this will help us in um, implementing an effective management technique. So if we know what is available now, and if we know what is going to be available in the future, then based on that we can vary this supply requirements, demand requirements, and conserve water. So for watershed modeling, we make use of watershed models of different kinds. And the major steps involved when it comes to watershed modeling is formulating the model, develop a model, develop equations, or make a model that is capable of running a particular condition. Then to calibrate the model, that is to fit the model such that it is related to the actual condition. So we have some parameters which are responsible for the water flowing. Then we have to make the model in such a way that it is mimicking the same conditions that are occurring in real time. Then we have to verify if that model, the outputs that is obtained from the model is correct. Then after that, we have to apply it in a real time situation. So these are the major steps that are involved in watershed modeling. So the correct answer for this question would be all of the above. Formulating the model, calibrating, then validating the model, then applying the model are the major steps involved in watershed modeling. So all of the above, option D would be the correct answer for this question. Moving on to the next question. Unit hydrograph is an example of what kind of a watershed model? So you can see in the options there are different kind of models which are watershed models: distributed, lumped, black box model. So unit hydrograph is what kind of a watershed model? Such a distributed model, lumped model, black box model, or okay. So let's check what all are these distributed models and lumped models and black box models and all. So when it comes to watershed models can be classified broadly into three categories: black box models, lumped models, and distributed models. Now, what are black box models? Black box models are nothing but uh, major components of the hydrological cycle, like rainfall and surface runoff. Say, if you're finding a relationship between them, if you are able to relate the if, rainfall is equal to some factor into surface runoff, or rainfall is equal to some factor divided by surface runoff, finding a relation between these two and then running and developing the model based on this is called comes under the black box model. So here there is no any mathematical relationship, but maybe empirically, by using a lot of data analysis, by running a lot of data, we will understand that okay, rainfall is equal to this many times the runoff. So such models are called black box models. Now distributed models on the other hand is when proper physical based equations are used to find out what rainfall is, find out what runoff is, find out what is the infiltration. So when proper equations are made use of for estimating or calculating, computing these processes, then such models that are developed based on these physical equations are called distributed models. Now, lumped models are something that takes an intermediate position between the black box and the distributed models. There are some portions of it which will involve equations, and some that is just making a relationship between the two components based on some data. So unit hydrograph approach is we have checked, we know what unit hydrograph is. It is a discharge versus time that is giving us an estimate of the surface runoff. Through the curve is giving us an idea about what is the surface runoff occurring. And unit hydrograph approach is an example of the black box model. So the question was, which category, under which category does this unit hydrograph approach fall under? It is a black box model. So the answer for this question would be option C, black box model. Moving on, which out of the following is not a major objective of the integrated watershed management approach? Okay, I'm sorry, the first two options are same. So out of this, which is not an objective of the integrated watershed management approach, is this question. Okay. So what is this integrated watershed management approach? So there has been a lot of, like I said, management techniques. So management techniques that are including a lot of it, not only just the water resources as an entity, but also uh, the the people that are involved, the socio-economical conditions that is arising as a result of the water resources, the availability of the resources, all of it together should be considered in order to develop management techniques for improving or conserving this water or to manage this water resources. So this is what is integrated watershed management. It's not just taking into account water resources alone, but it is also taking into account the people who are using it, the finances that come with it, the availability of the resources, all of it together. So major objectives of this integrated watershed management approach, which can be in short form said as IWM, has that water, it has got multiple uses. So it has to be managed in an integrated way. It should also be managed at the lowest appropriate level, and it should take into account all of those people's interests or all of the areas in this world that is making use of water. And it should be treated as an economic good. It should not be taken as something that is plentifully available, but it has to be taken as something that has got good economic value. So these are the major objectives of integrated watershed management approach. So the question here was, which is not a major objective. The answer is water allocation should be localized. So it shouldn't be localized. Water management, water allocation should not be taken into consideration, or not only the immediate surrounding or immediate requirements have to be taken into consideration, but what happens if suppose some problem happens with the availability of water in a particular region, how is it going to impact the subsequent regions or faraway areas? This also has to be taken into account. So it should not, the water allocation or the requirement of a particular area alone is not to be considered. There has to be a larger consideration of the water, so it should not be localized, and that is one of the major objectives. So here the option is water allocation should be localized, which is wrong. So the correct answer for this would be option D. Moving on, which out of the following is not a strategy of the integrated watershed management approach? So in order to achieve, we just checked it, what are the objectives of integrated watershed management approach, which is not localizing the water allocation. Water has got plenty of use, so it has to be considered, the management has to be done in an integrated way. All of the people and all of the uses for which water is done should be taken into account, and it has to be looked upon as an economic goods and given important value. Now, what are the strategies that are used for integrated watershed management approach? There are various strategies, and out of this, one is not a strategy. So, which out of the following is not a strategy is the question. Is it a long-term viable, sustainable future for basin stakeholders? Non-equitable access to water resources, application of principle of demand management for efficient utilization and prevention of further environmental degradation and the restoration of degraded resources. Which out of this is not a strategy adopted? Okay, so some of the strategies that are adopted in integrated watershed management as a long-term viable, sustainable future for basin stakeholders, which means that the sustainable management of water resources, we had checked sustainable, non-sustainable practices. So sustainable water use, sustainable management techniques have to be used for conserving or preserving or protecting the water resources, so that in the future also the people belonging to an area can make use of the water. It's not just taking care of the immediate requirements of water. Then equitable access to water resources for all water resources. So water availability should be made equally accessible to all sectors of the society, all of the regions in the way that is required by them. There should not be any discrimination when it comes to access to being able to access water resources. Then application of demand management, principles of demand management when it comes to efficient utilization of efficient utilization of water resources. Then prevention of environmental degradation or and as well as restoring the degraded water resources are these few are the strategies that are implemented when it comes to integrated watershed management. So the question was, which out of the following is not a strategy? Option B is the correct answer. Non-equitable access to water resources is not the correct statement. The water resources have to be an equitable commodity. It has to be available to everyone without any grounds of discrimination. Everyone, every area, every sector in the quantity that is required by them. So the correct answer for this question would be option B, non-equitable access to water resources for all water uses. Moving on. Which out of the following is an example of for indirect recharge of groundwater? We had did a question that is relating to this earlier. So which is an example for indirect recharge? Is it excess rainfall, surface water seepage, aquitard leakage, or wastewater return? Okay. So we did see what all are the different classifications of recharge. Artificial recharge involves irrigation losses and wastewater return. Natural recharge includes rainfall, recharge to rainfall and recharge through these effluent streams. Indirect recharges including acute leakage. So here they have asked an example for indirect recharge, which is option C, acute leakage. Moving on, which out of the following is not a groundwater management technique? So there are various groundwater management techniques, which out of the following is not one technique for managing efficient management of groundwater resources. So conjunctive use of surface water and groundwater, artificial recharge of groundwater, overpumping of groundwater, or intra-basin transfer of water. Which out of this is not a groundwater management technique is the question. Okay. So groundwater management techniques, there are various groundwater management techniques. Some of the useful management techniques we saw is the conjunctive use of surface water and groundwater. That is including the surface as well as the groundwater when it comes to making programs. Then artificial recharge of groundwater and seawater barriers. Again, that is something like filling in recharging empty dug wells or underground structures for future uses. Another technique of groundwater management, interbasin transfer of water, that is from one watershed to another, and intrabasin transfer of water, that is within a basin itself or within a watershed itself, uh, transferring water from one sub watershed to another watershed, or developing infrastructures for that. It can be a distribution network, or it can be routing the water or canal systems or whatever it can. Then there is indirect recharge through avoidance of pumping. So allowing water to naturally refill and reducing the amount of pumping is one way of management of groundwater. Then there are some strategy or some method for control well fields, which we'll look in the coming slides. So these are the different groundwater management techniques. Question here was, which is not a groundwater management technique. Option C would be the right answer, over pumping of groundwater. That is not groundwater management technique. It is exploitation of groundwater, unnecessary exploitation of groundwater. When you pump excessive amounts of groundwater, depletion of the groundwater resources. So option C, over pumping of groundwater is not a management technique. Whereas options A, B, and D are. Moving on, wellhead protection strategy falls under what kind of groundwater management technique? We just now saw there are around six very useful groundwater management techniques, which involves conjunctive use of surface water and groundwater, artificial recharge, interbasin transfer of water, intrabasin transfer of water. Then there is avoiding pumping of water. Then again, there is control wells. So out of the six, under which category does wellhead protection strategy fall? Okay. So there was this groundwater management techniques called control well fields. So what are these control well fields? These are nothing but the wells are strategically placed so that the hydraulic gradient can be manipulated such that there is no excessive usage of water or excessive very less availability of water. So, so that these wells, that is placing such wells will help in giving a direction to the usage of groundwater. So this technique is called the control well field. Control well field is nothing but we are placing certain wells in between. Say there are two wells and we are placing another two wells in between so that the gradient of the water can be manipulated. So wellhead protection strategy comes under this control well piece. You can see here it is helping induce desirable groundwater flow direction. So when we place water wells in between or in desired locations by estimating what is the groundwater flow, what is the slope of that area, what is the quantity of groundwater, what is the kind of aquifer there, how is transfer of water, how is the transport of water occurring through this aquifer. Based on all of that analysis, if we can place a well so that the direction can also be manipulated by us, then such techniques are called control well fields. And an example of this is wellhead protection. So the correct answer for this question would be option D, wellhead protection strategy falls under control wells. Okay. So that was about the questions associated with the week 10 lectures that can help you solve the week 10 problems an assignment. Now, moving on to some questions that require discussion regarding questions that had come in assignment 9. Remaining of it are pretty straightforward as well as discussed in the problem solving session. Some numericals and questions were not discussed by me, so I thought I'd discuss that in the class as well. So question number 2 in assignment 9 we've been asked to find the change in storage where an aquifer of 150 hectare area receives 108 mm of water and duration of this rainfall is 1 day. They have also given that water is draining out. The outflow rate is 1.5 meter cube per second. So what would be the change in storage is the question. Okay. So here they've given making use of this water balance equation, that is net inflow minus net outflow is equal to change in storage. We can compute this. So they have provided the area as 150 hectares. We require to convert it to meter square because the answer that is provided here is in millimeter. So in order to arrive at that, we have to either convert it to millimeter or meter. Since hectare is a large unit, let's convert it to meter in terms of meter first, and then we'll convert it to mm. So area is 150 hectares. 1 hectare is equal to 10 to the power 4 meter square. So multiplying 150 by 10 to the power 4, we get 115 lakh meter square. They have also said that the area is getting a rainfall of 108 mm. So this will be the inflow depth. What they have asked is a change in storage, that is also in mm. So the hint from this question is we have to get the answer in mm. So in order to do that, we have to convert this inflow as well as the outflow values into mm. Now they have said inflow is 108 mm. The inflow is occurring for a period of 1 day. So 1 day again we need to convert it in terms of seconds because outflow rate is given in meter cube per second. So when we do the computation, we'll require to convert this into seconds. So 1 day is equal to 86,400 seconds. When you multiply 24 hours, 60 minutes, 60 seconds. Now outflow rate, they have said it is 1.5 meter cube per second. Since we need the answer in mm, we are supposed to convert this into depth, units of depth. So in order to do that, what we'll do is we'll first multiply it with by time so that we get the outflow volume. So 1.45 into 86,400 will give us 12 lakh 9 sorry 1 lakh 29,600 meter cube. So when you multiply the rate with the time, you will get the outflow volume. Now, when you divide the outflow volume by the area through which the outflow is occurring, which is nothing but volume is 1,29,600 and area is 15 lakh. When you divide these two quantities, you will get the outflow depth in meters. Be careful of the units. We started with meter, we are getting it in meter. Now the answer we require in mm. So in order to, for that, we'll convert this into a millimeter, multiply it by 1000, we will get the outflow depth is 86.4 mm. Now we know the rainfall, which is the inflow. We know the outflow depth, which is 86.4. So inflow minus outflow, 108 minus 86.4 will give 21.6 mm, which is option A in the question. So the correct answer for this question would be option A. Now, question 3, what is the mathematical expression to calculate groundwater development in percentage? So, the groundwater development in percentage, there are various steps to in order to calculate the recharge. So out of that, the step 5 that involves groundwater development percentage is equal to the net draft divided by the average TARR into 100. So the answer would be option C, net draft by average TARR into 100. Now question number 8. In the groundwater assessment unit, which subunit comprises of areas with ground slopes greater than 20% and has practically negligible groundwater recharge? So we had discussed about what groundwater assessment unit is. So whenever we need to develop a management technique, like we discussed in today's problem solving session, it is necessary that we divide the areas into certain standard units. So when it comes to groundwater recharge estimation, the standard units that is used is groundwater assessment unit. Now, groundwater assessment units are again divided into subunits. So, which subunit is comprising of areas with ground slopes greater than 20% and negligible groundwater recharge is the question. So, like I said, groundwater assessment units of a state or a union territory, it is classified into block, taluk, mandal, and watershed. So, all this block, taluk, and mandal, these are more administrative in nature. That is based on the administrative boundaries. But watershed is based on the hydrological. That I said, watershed is nothing but when it rains, when all of the water that is coming in that area is draining into a particular network of streams, then that area is called watershed. So first three ABC, block, taluk, and mandal are more of administrative units, whereas the fourth one, watershed, is a hydrological unit. And these are the groundwater assessment units. Now, groundwater assessment units are further classified into subunits. Now, every block area or every block has got a subunit of hilly area, a subunit that comprises of poor groundwater quality, sub area that is called command area, and a subunit that is called non-command area. Now, what are these hilly area and all of this we'll see. So hilly area is nothing but a subunit which has ground slopes that are greater than 20%. And not only that, they have negligible groundwater recharge. So no groundwater assessment is made for it because there is no recharge is there. Groundwater assessment is nothing but an area for which the groundwater recharge estimation is made. So such areas have slopes that are greater than 20%, and not only that, the groundwater recharge is negligible. So our answer would be this. The subunit is called a hilly area. Now, what is poor groundwater quality area? It is nothing but a subunit that comes under the ground assessment unit where groundwater recharge is possible, but the quality is very bad. The quality of groundwater available in that region is poor. So such sub classification or such areas are called poor groundwater quality area. Now, there is a subunit called command area. Command area is an area in this groundwater assessment unit where the groundwater quality and all is very good, and also the there are structures like canals and ponds and tanks that are making use of surface water. Surface water irrigation is occurring in such areas. So such areas are called command areas. So definitely surface water irrigation will have these structures, surface water structures like canals, a network of canals. There will be ponds, there will be tanks and all in this area. Here, not only is the groundwater quality good, but surface water irrigation is also considered. Now, there is area where the groundwater quality is good, but surface water irrigation is not considered. So these areas, surface water irrigation will not occur. Not only that, these structures and all won't be there. So these are the four sub-unit classifications of groundwater assessment unit. I'll just go through them once again. Groundwater assessment units are classified, the classifications of groundwater assessment units for a state can be classified as blocks, taluks, mandal, and watershed. Now, each block can have subunits called each block, each taluk, each mandal will have subunits called the hilly area, poor groundwater quality area, command area, non-command area. The important point when it comes to hilly area is the subunit is comprising of area that has slopes greater than 20%, and not only that, there is negligible groundwater recharge in this. Poor groundwater quality area, the groundwater quality is poor. Command area, groundwater quality is good and surface water irrigation is used. Non-command area, groundwater quality is good but no surface water irrigation. So this question, the answer would be D, hilly area, because subunit that is comprising of areas with ground slopes greater than 20% and has practically negligible groundwater recharge. Option D would be the right answer. So that's it for today's classes. If you have any doubts regarding the questions that are discussed today, please feel free to ask. I'll be around for some more time. Otherwise, you're free to leave the session. For those of you who have joined late, you can go through the questions, and if you have any doubt regarding that, you can ask, or we can meet in the next class. Setu, you will get the announcement. I mean, through mail. I mean, whatever announcement is made, notifications will be. You will obtain the notification. I have no direct information about when it will be announced. If I get anything, I'll discuss it in the during the problem when I meet you online or during the problem solving session. For the last 5 to 10 minutes, I'll be rerunning the slides so that you can do it using the video itself for 10 seconds each slide, so you can practice the problems on your own. So we'll be ending today's session. Thank you for attending the session and see you next week. Bye bye. Have a great weekend.